Okay, good afternoon. I will report some oscillation results from the experiment. And so we all know the neutrino physics, and reactor actually has a very long history, since 1956, which was the first observation of the neutrino event. Then going through, series actually. Those experiments near the reactors, basically you can see that some detector actually it was actually quite not very large, so then become larger and larger. So the Darbee experiment was proposed in around 2006, and the aim is really try to measure, or that time trying to search for the theta 1,3, the third mixing angle. Of course, we will need all the mixing angle be measured before actually you can really explore so-called the CP violation in the neutrino sector. So we all know we have 3 generation neutrinos. Okay, this is from the lab experiment. You can see the Z peaks you can fit with the 3 generation. And so we, basically now we actually complete all the quarks and the lepton sectors, plus the Higgs and the force carriers in the standard model. The neutrino, we call it neutrino revolution, actually has a lot to do with the so-called neutrino oscillation. It's been discovered, okay, through the, we can see the solar neutrino type experiment like SNO, and also the atmospheric type experiment like Super K. So these are quite clear. Okay, the neutrinos actually oscillate, from the source to the place we detect them. Now, the observation of neutrino oscillation, of course, implies the neutrino, do have mass, and typically, we will have so-called the flavor eigenstate, which is a mixture of the so-called mass eigenstate, and these are the matrix, which has 3 mixing angles and 1 phase, and very roughly you can see we have the so-called this is type, disappearing type experiment. The probability of nu E bar from the say reactor neutrinos nu E bar to nu E bar at the detector site, then it's 1 minus the sine squared 2 theta 1,3 times this is amplitude times the oscillation, the frequencies, which is proportional sine squared delta m32 squared times the distance length divided by the energies. So the delta m32 square basically is the mass square differences. Okay, we call the mass splittings. So the full matrix, of course, quite some time ago, we already knew from the Maki, Nakagawa, Sakata, and Pontecorvo. So this is a unitary matrix, has 3 mixing angles and 1 CP violating phase, and you typically also can put in the so-called marijuana phases. Okay, so basically, various experiment and probing different parameters, which you can see from the atmospheric and accelerator, and get the theta 2,3 about 45 degrees, and and the delta m32 squared is about 2.4 times 10 to the minus 3 eV squared, and then the theta 1,3, of course, the one in 2006, we're trying to basically propose the experiment to measure the Darbee experiment, and also like Reynolds and double shells. And theta 1,2 is about 32 degrees. It's from the SNO, solar, basically chem length, the solar neutrino type, and get delta m 2 1 squared about 7.9 times 10 minus 5 eV squared. So basically, from this mixing matrix, we can find out, the mass eigenstate, which has, the different proportion of the flavor in there. Then this is basically from the mass splittings, and also you can see the CP violation, if we actually can do the experiment, will be proportional to those angles times the CP phase. So, of course, the neutrino is very hard to measure, It's weak interactions, and the event rate typically is not very high. So it took a long time, to get us to this point. But still, it's pretty incomplete in some sense. We still don't know, okay, the mass hierarchy is the inverted or normal, and it can be either way. And because we only know its mass square differences. And for example, theta 2,3, is that exactly pi over 4 or not? We don't know. And it's very close. And of course, there are other, important aspect of a CP violation. It's conserving or is violated, or CPT, and its neutrino is its own antiparticle or not. It's like marijuana type. Is there any more, heavier or stereotype neutrinos? Anyway, the list can go on. So to search the theta 1,3, of course, the Dade was designed to do this, and basically, this before we had measurement. This, I think it's 2011, 12, and that time the sin squared 231.3 has only a limit about 0.15. This is from the Shell's experiment. So the principle to measure, actually try to get a good measurement, more precise measurement, and not only we use the reactor antineutrino as a source, we also need to measure the so-called disappearance based on so-called near site, near detector, compared with the far site. So basically, the near site is very close to the reactor source, so serve as like a flux measurement normalization. But then the far side, if there's any oscillations, then will show up. So basically, that's the idea. And typically, this distance for theta 1,3 is about 1 to 2 kilometers. So I think design experiment close to about 1.5 kilometers. So basically, this from the previous limit, we know it's a small effect. And actually, before we get any measurement, okay, we don't know how large. The theory has a variety of spectrum, and it could be very small, like less than 0.01. Anyway, the key is try to maintain a very good control on systematics, so we actually can do the measurement if the value is sizable. Anyway, the precise measurement based on these factors. So in the design, we have to optimize our baseline. Actually, this is it's a pretty broad optimization. We need a high statistics. That means need a powerful reactor, and we need large enough detector in the very long run. And we also try to control systematics based on the near and far ratios. You can see a lot of the factors can be cancelled out, which including, for example, detector related. If we can do the identical design of detectors as much as possible, and also we need pretty good calibration, and also the reactor related stuff, which can also cancel out. Then the background reduction, of course, we need to shield the nearby effect, for example, radioactive backgrounds, and also the cosmic rays. And so this is based on the water shield. Also, we need to put underneath the tongue. Okay, so the Dave collaboration actually consists of almost 230 collaborators, and Asia has about 21 institutions right now, and Taiwan we have three institutions from National Taiwan University, National Jiaotong University, and also National United University. Europe we have two from Czechoslovakia and Russia, and also American has 17 institutions, and also right now we have one from South America, Chile. The site at Daya Bay, which is in the southern China in Guangdong, about 50 kilometers from Hong Kong, I think, on the east side. So you can see it's right next to the shore. It's pretty good, geology with the mountains nearby. So the design is that we have, because there's a total of 6 reactors here. You can see the Daya Bay reactor is a pair, Ling-Ao and Ling-Ao 2. Actually, I think Ling-Ao 3 probably somewhere here. It's in construction. And so we built, 2 near detect holes. Each detect hole we would like to put in 2, side by side, the detectors. And the far side, which is we call EH3, has 4 detectors there. And you can see the overburden. Okay, the far side is about 860 meter water equivalent, and the baseline to the far side is about 1.6 kilometer, and both near sides about 500 meters away, 360 to 500, and with a smaller, about 250, 260 meter water equivalent shieldings. So basically we try to build 8 identical detectors positioned in those locations, and basically try to sample the reactor anti-neutrino flux in the near and far holes, and then you can see these are actually the right at the bisector of those nearby reactors. Then we look for the evidence for disappearance. Then so far, since end of 2011, actually just before is the Christmas, I think, we start taking data with the so-called 6 detectors at that time, and to 2012, summer. So these are the early data, which we actually made, number of publication already, and also the measurement. And then we finished the other 2 in 2012 in October. And since then, we're actually taking so-called A80 data. I will show some of the data in this period too. So the reactor antineutrinos basically is from the fission process. Actually, these are the dominant contribution from uranium-238, 235, and plutonium-2. And typically, I think those spectra probably can go to about a few percent level. And there's also time dependent because they feel burning. So these actually need some models. But basically, with a 3 gigawatt thermal power, it can generate about 6 times 10 to the 20 antineutrinos per second. Okay, so it's a large number of flux. And this is the photo you can see in the Abe site. Our detector actually underneath this mountain, and that's the so-called entrance going in with the tunnels. And these are the reactor sites. So basically, it's the top 5 most powerful reactor complex in the world. The detection actually is pretty simple. The method is using so-called inversibility decay. And you can see the antineutrino come in and interact with the proton and produce the positron and neutron. And the issue is try to measure both signals. So the positron will annihilate right away. It's a prompt signal, and with some kinetic energy. But the neutrons will basically scattered until get absorbed. There are 2, channel absorptions, because we add, in our target volume detectors, about 0.1% gadolinium, and with large cross section, so it has the time is about 300 microseconds, and it generates about 8 MeV delay signal gammas. Then the protons actually can also absorb basically the neutrons make into deuteron plus the 2.2 MeV gamma rays. So both of these actually we have done some the measurement. The detector actually, as I said, we built 8 anti-neutrino detectors, and it's a 3-zone cylinder. You can see the 3 meter inside the target volume. We call inner acrylic. It's a gadolinium doped liquid cylinder, about 20-ton mass. Then the outside is the outer acrylic. It's just a liquid cylinder, about 20 ton. We call gamma catcher. Then the outside, that's the in the mineral oil region. That's a stainless steel tank. Basically with 40 tons mineral oils. Then with a full 192 8-inch PMTs surround the cylinder detector, and the whole thing, okay, basically the energy resolution about 7.5% over reading. Then this is the inside of the one detector before we fill with the liquids. You can see these are the 8-inch PMTs with the black, the shield, and inside with 2 layers. The innermost, the 3-meter one, was built. All 8 of them were built in Taiwan. And so the Diode anti-neutrino detector, those ADs are immersed in the at least 2.5 meters of water, I think. So basically, these are instrumented inside. So it's a water Cherenkov detector to look, basically as additional rejection for those customary muons, and also for the shieldings. And on the top we have 4 layers of RPCs. So you can see this is those water Cherenkov PMTs. Some of the installation, you can see this is the EH1 near hole. We install those detector. It's a 5 meters, okay. So with the calibration units on top, then we fill the water, and to 1 week. Then we put the RPC roll in, then we actually put the cover up. This is the far hole. Far hole, you can see the 4 detector was installed that time. It's 2012, I think October. We start feeding the water. And as I said, okay, we now have collected quite a bit number of days of data. This is the so-called the first 621 days of data, and it's over 1 million anti-neutrino interactions already. And even at the far side is about 150K. And you can also see, the reactors signals. They actually have on-off cycles in this timeline. The measurement, of course, how do we measure? A spectral measurement will allow us to measure both TL13 and mass splitting. And basically, if we can measure so-called the positron energy, or which can be translated to the neutrino energy, then you can see the near side, far side. Of course, after normalization, with or without the oscillation, you can see far side may have differences. So basically, we try to extract out the so-called θ13 with this amplitude, and also this frequencies will be correspond to so-called the delta E square. Okay, delta E square actually, this term actually in here actually is more complex. Then basically it's roughly delta E square is about delta M 3, 2 squared plus minus, this depend on the hierarchies, okay, of 5.2 times 10 to the minus 5 eV squared. Okay, so the energy calibration, of course, if we do try to do the spectrum type the measurement, is very important. And we don't have a lot of handles. And you can see these are the one of the examples of the, we actually have quite a number of sources in the calibration source, plus some of the in situ type, the so-called like spallation type, the NGD and H type signals. So you can see we compared various different. This is the total 8 different ADs, and they're all within 0.2% band. So, and of course, you can see the reconstraint energies. And still, we don't have continuous one. The spallation neutron, you can also see the 8 MeV, very clear, NGD, and plus a 2.2 MeV there. We also need to basically try to relate the so-called reconstructed energy to the true energies. And this has to go through, so-called our energy response model. And this is the one which basically we try to use our detector and also those calibration source, try to extract out what's our uncertainty there and what's the model dependence. And basically you have to go through simulation response. There's a various effect and also readout electronics effect, including the charge collection efficiency, those things. So anyway, this is after quite a bit work, and you can see this is various different kind of calibration points. This is the I think between the basically about half MeV all the way to about 8 MeV. And this is the curve. And you can see this is from 0.9 to 1.1, okay? And those data points actually line on this curve. It's quite nicely with a few, you can still see, the differences. And so we can do the combined fit with those so-called the monogenic gamma rays peaks. And also we can use so-called one of the continuum beta decay spectrum in our detectors from boron 12, and the boron 12 covers from about 4 MeV all the way to about and basically about 15 MeV level. So this also tells us how good is our calibration curve, and you can see there's a boron 12 and also nitrogen 12 contributions, and these are the two main contributions with data. Then our model basically you can see is less than 1% uncertainties correlated among all the detectors, and we say we cross-validate also with the other type of beta decays, and this is our so-called the response model with uncertainty of the band. And the near and far comparison, of course, once we finish this, we have the selection of so-called the prominent delay coincidence. Then you can just count, for example, this the baseline versus the detected the rate, and the near side actually is about 0.98, little more than 0.98, and the far side you can see it's go down to about 0.93 level. So this is the observed the relative rate deficit and the relative spectrum distortion. Over here you can see, and this is our near and far ratio. So the oscillation result, this is still very preliminary because I think we present this probably just before summer, just the summer conference, but we still haven't actually published this yet. This is based on 621 days, and the sine squared 2 theta 1 3, and you can see the error actually reduced, but the number also will have some shift because it's about 0.084 right now. But it has very nice also the so-called the measurement on delta m E squared. And basically, you can see this is the sine squared 2 theta 1 3, and also delta m E squared with the chi-squared contour. So we're still checking, okay, this result, and we'll try to because this is more precise than we had it before. This is the one we published actually in February in QRL. This is based on radiant spectrum. You can see that time, the sine squared 2 theta 1 3 is 12.9, and the error bar that time is almost twice bigger. And of course, this is the delta m E squared. So with more and more data, of course, the analysis becomes much harder, and we have to dig more details and look for the consistencies or try to resolve some inconsistent problems. These are this is another independent measurement from the so-called NH. The neutron captured by the proton, the hydrogen, and you can see it actually shows up quite nicely. But statistics actually is not as good as the Caledonian. So it has actually served as a very good check because it has to go through a very different analysis. Also has a very different, so-called the prediction volume, because even the 4 meter we call the gamma catcher, we can also have those NH events. So the distribution is quite different. But this analysis actually we use only the 680s so far, with the 217 days period, and the result comes out about 0.083, plus minus 0.018. So error is much larger, but it's consistent with our measurement of NGDs. Now, to do this oscillation measurement, we're assuming 3 flavors of the neutrinos. We can also check is there any stirred neutrino, the fourth one. So the stirred neutrino, of course, is one of the leading candidates to resolve these so-called outstanding puzzles in the astronomy and cosmologies. And so basically, it looks like we may have some handles and to look if we want to search or look for it. Anyway, basically the searching for the stirred neutrino in Dave, we cannot study the stirred neutrino while they're interaction in the detectors because they're stirred, okay? But if they mix with the 3 other flavors, their presence can be detected. So there's assumption about the mixing of the 4th type, stirred neutrino. So based on that, the so-called mixings, we actually can set up the so-called sensitivities. You can see based on the our detector, and these are basically our data. You can see if we superimpose some of the oscillation term of the stirred neutrino. So the searching basically makes the formula more complicated. You can see adding the theta 1,4, and also with sine squared 2 theta 1,4 times this also sine squared delta n 4 squared, okay, term, and besides the usual ones. So based on this, we actually can set some the so-called exclusion contour. This is sine squared 2 theta 1,4 versus the delta m 4 squared, okay, the absolute value. So the sensitivity is largely explored in so-called delta m 4 squared less than 0.1 electron volt, okay. So basically we have some sensitivity here. The early ones you can see is from other experiments. And to illustrate that, what we look like in our detector, these are the so-called one of the near side and the far side, and you can compare with the so-called 3 neutrino best fit, and also this curve, that's the fourth one. Okay, if it's as large as 4 times 10 to the minus 2 eV squared. So the result actually we just published in October, and I think this is the one. So you can see this are exclusion contour. This is bogies, and we actually set two 95% contour. One based on the foam cousin, the other one is the solid ones are. So basically, you can see this has a good coverage between 10 to the minus 3 eV squared to 0.1 eV squared. We also have, with this large statistics, high static data set, and we actually can measure so-called the reactive antineutrino spectrum. Reactive antineutrino spectrum, why do I measure? Of course, it's because there's possible so-called the reactive antineutrino anomalies, and this actually shows up. Okay, so I think my time is up. So I'm very quickly. Basically, the idea is, I mean, the reactors has some kind of models, and those models actually has actually different type models. And when you compare them, actually, you will find out they have at least 3 to 5% uncertainties. But our statistic actually can get down to 1%. So we actually do compare them. So this is the one of the spectrum shape, and we try to compare different model. You can see the spectrum shape is smooth, but however, okay, around 5, MeV region seems to have some, things we cannot quite explain by these two models anyway. So we have about 4 to 6 MeV region have a little bit, very small axis here. We don't know what is. Maybe the imperfection of the model, maybe something else. But it's about 4 sigma level. And this actually has been seen also not just us, by Doubleshell, by Reno. I think they all have some imperfection here. It's very small, I think less than % level. So what is? We actually don't quite know. There's various things we try to explore, but some of them are definitely disfavored. For example, we said here, some of them because we do have good spectrum like a boron 12. Okay, we don't see bumps there. Why it showed up here? Also cannot be explained by a single beta branch and those lines. So anyway, our goal actually is just try to publish this, present it when we have a good statistics, and for the the theorists try to see is the reactor model or not. So you can see we can actually try to unfold so-called the positron spectrum to the antineutrino spectrums, and we can compare with the models. Okay, so my summary. Okay, the Derby so far with a large θ13 we have very rich neutrino physics so far. We have a precision measurement of the oscillation parameter both at θ13 also the delta ME squared. And also we can search for this third neutrino. We have high statistics for the flux and spectral measurement of reactor antineutrino. We also may have other physics we're looking for. For example, supernova. Okay. Anyway, with two or three more years data dating, we plan to take data at least up to 2017, maybe even more, and that will get us to very precise measurements on those parameters. Of course, we expect the more result, and this is sensitivity from the sin squared θ13. You can definitely see once this is the 6, I think, reactors, 80s and plus 8 80s, and now we actually can go all the way down to less than 0.01. So, okay, So thanks. So I think I'll stop here.
Any questions?
Yes. How does it work? We only measure the electron type. Okay, so there's assumption we can only be sensitive to that. Pardon me? 4-1, yes. That's between the right, the third neutrino and the first neutrino. Yeah, in one. Yes.
More questions? Actually, I have one question. I heard that following up a project of diabet experiment named Juno has been approved by the central government of China. So here, can you say something about the Juno?
Yeah, well, we're still in the proposal design phase of the Juno experiment, even though, of course, there's a good promise from China. And also the collaboration, I think, just formed in the summer, which including more collaborators from Europe, like Germany, France, and Italy. But maybe I can show you a little bit. Okay, so the Juno actually will be a new site. The database over here, you can see these are actually all reactor sites along the shore. Originally, we would like to put some detector, somewhere here. Somewhere here, that's right. But then there's several reactors here which complicate the problem. And so finally, actually, it was decided to choose the new site here. And the site actually looks good. And looks like we will have the first so-called groundbreaking in January, early January next year. And there are two reactors complex. One's Yangjiang, the other one is Taishan. And so this is like, like unilateral triangles, and about 60 kilometers away from each. And so you can see these two. Okay, they actually not only under construction, they actually I think start operating. So they will have pretty good thermal power. But to detect, this is try to measure so-called the mass hierarchies. And to measure the mass hierarchies, and it's U-T 1, 2, I think, then we need a very large, because it's a 60 kilometer away, very large detector. This is 20 kilotons liquid centimeter with about 35 meters across, So this is not, this is very, very challenging, okay? Nobody has done this before. And this size. So we would like to have this one underground, so this has to be 700 meters underground. And then we will have the so-called the water, shielding in here with the liquid cylinder in the middle. So all these right now under design, and there's a lot of challenge here because to measure this actually we need to look for the spectral distortions between so-called the normal hierarchy and the inverted hierarchy, and that actually when you sit right at the so-called the apex of these two reactors complex, and basically you will see so-called this kind like spectrum shape, this interference shape, shiftings, depending on which one. So it needs very good so-called the energy resolution, 3%, and which is much tighter than so-called the okay, the last one. Okay, it needs a 3% energy resolution or better, and so far right now, Dave will only achieve about 5 to 6%. Okay, at best. So this is a much larger detector. So this is not a trivial, not very trivial. And it's, with this kind of so-called experimental hole constructions and the detector size of this detector, and it will be probably, will need roughly 7 to 10 years preparation. Okay, and then we'll have to run minimum 3 years, 3 to 5 years. This is assuming we can achieve the energy resolution we claim.
Okay, let's thank the speaker again.